All right, hi everyone, this is Dan Barry, and welcome to this webinar titled Unified Water Modeling Droughts, Floods, Fish. So this is continuing a theme. We've had a couple other webinars in this sub-series in the MAP webinar series on unified modeling. We had a webinar in the fall on the topic of weather and climate unified modeling, so unifying the modeling efforts across timescales, and then we also had a webinar that was specifically focused on marine applications and unified modeling for different applications in marine ecosystems and sea level as well. And so this is continuing that theme. It's a kind of a broad look at different aquatic systems or water modeling in particular. So we're going to hear talks that cover the hydroclimate, including a focus on drought, also flooding and extreme precipitation, and then marine ecosystems. And we'll hear from 4 speakers on those topics. So we're going to hear first from Krista Peters-Lagarde, who's at NASA Goddard, and she's going to talk about their NLDAS work, North American Land Data Assimilation System work, which is relevant to drought monitoring. Ed Clark is going to talk about the National Water Model, which is a new hydrological model that NOAA is running on the operational side. Gabriella Villarini from the University of Iowa is going to talk about some of the work he's been doing with NMME, looking at precip and temperature and also extreme precipitation events. And then Brian Wells from the NOAA Southwest Fisheries Science Center is going to talk a little bit about the work he's been doing in the coastal California current system. So a nice diverse group of talks, and the way that we run this is we'll do the talks each about 12 minutes, and then after each of the talks have a little bit of time for some question and answer. And if you're logged into the webinar, we ask that you send me a chat message if you have a question. You don't have to type out the whole question. You can just tell me you have a question. And then what I'll do is I'll unmute your line, and you can ask the question of the presenter that it's targeted towards. So without further ado, I think we'll switch over to Krista. Krista, are you there?
Yes, I am.
Okay, great. So Krista, I just passed presenter rights over to you.
Okay. I just shared my screen.
Yeah, that's great. And yeah, whenever you're ready, go ahead.
Okay, great. Just a little advertisement here. We have a Twitter account now for NASA_list if you're interested in following us. Okay, so here's my talk. All right, so the title of the talk is Similarity Assessment of NLDAS Model Outputs for Drought Estimation, and I want to acknowledge my co-authors, David Mako, who's on, Sujay Kumar, Shugang Wen, Yilong Xia, and Mike Eck. And this project really builds on the success of NLDAS, as you mentioned earlier, and there's been contributions from many people on the NLDAS and LIST teams over the last 15 years. So thanks to all of them, and thanks to the MAP program for support. So the overarching question I want to answer in this brief presentation is, what is the value of each model in the ensemble when you're monitoring drought? Okay, so a little bit of background. The current NLDAS system consists of 4 different models, and we run these models over the continental U.S. at an 8th degree resolution, and so there's the NOAA LSM, Mosaic, Sacramento, and VIC. Those are the 4 existing models, and this is an ensemble mean of soil moisture percentile for the total column soil moisture. Okay, and this is just one example of the type of products that are used for drought monitoring from the North American Land Data Assimilation System. And here's a URL if you want to go click on that. You can see the actual current products. Okay, so one of the things that we've been doing with NLDAS is trying to understand how, which variables in NLDAS are relevant for drought monitoring. I mean, soil moisture is kind of an obvious one, but there's other outputs from NLDAS like SWE, evapotranspiration, runoff, and so on. And so Yulong actually did a study where he basically constructed an objective drought monitor from NLDAS using 5 different variables, which were soil moisture, evapotranspiration, runoff, and precipitation. And these results just kind of showed us that, if you look at this third row, these are objective blended drought indices from NLDAS, and if you look at the fourth row, that is the U.S. Drought Monitor, and it's just some examples showing how when you combine these variables and you weight them in a certain way, you can mimic the drought monitor, not perfectly, but to a fair degree, as compared to the top row, which shows soil moisture in the top 1 meter, for example. So just an example of the kind of work we've been doing. And, you know, and this is, of course, the entire ensemble. So one of the questions that we had was, well, you know, how much does each model add to that ensemble, and how could you look at the contributions of each model to different variables that are relevant to drought? So we are currently working on the next phase of NLDAS, and we're trying to use some updated models and as well as data assimilation. I'm not going to talk about data assimilation today, so all of the results I'm showing you are for models without data assimilation, okay? But the 4 new models that we're working on for NLDAS for the next phase are shown here in the middle. So there's NOAA version 3.6, NOAA MP version 3.6, catchment land surface model, which is the same land model that is used in the GMAO, GEOS5, and MERA2, and then VIC. So this is just a new version of VIC, okay? And so what I'm going to talk about today are really these models and how these models compare to the previous models. So these results are from what we call the NLDAS Science Testbed. So we've been evaluating the ability of these new models against the old models for different variables that we know are important for drought. So one of the first graph over here, if you focus on the left-hand side, just to kind of get a sense for what you're looking at, the operational NLDAS, these are the same 4 models that I showed you earlier, Mosaic, NOAA 2.8, STAC, and an older version of VIC, are shown here, and it's anomaly correlation against the scan data surface soil moisture at 117 sites. So this is the anomaly correlations we have today, which range from about 0.5 to about 0.7. If you look over here, everything over here are the new models that we are testing as part of our test bed to see whether they are good candidates for the next generation NLDAS. And you can see here that we've got the catchment model, that's the purple, and we have different versions of NOAA all the way from 3.2 to 3.6, and they all behave pretty similarly in terms of soil moisture. Then we've got the NOAA MPs. We have 3 different versions of NOAA MP with different physics options. And so the one that is the most similar to the default is this sort of yellow-orange line. The dynamic vegetation is this green line, and that's the version we're going to be looking at a little bit later. So this one has not only dynamic vegetation, but it also has a simple treatment of groundwater. Both of these green ones do. It's a top model-based groundwater scheme. This is not the latest scheme that is currently available, which is the Miguez Macho and Fan Busanesque scheme. This is a simpler scheme. This is from GoAway News' original work with NOAA MP. Okay, and then the last column is VIC. So this is the new VIC, and you can see VIC has always been lower in skill for soil moisture, and that kind of continues with this version. But if you look over here at Streamflow, and this is for unregulated basins, 572 unregulated basins, you can see that VIC has traditionally been the strongest in terms of Streamflow, and it continues that in the new version. So the bottom line, though, when you look at these results, the first thing you probably notice is that the behavior of this new ensemble is not very different from the old ensemble. And that's what led us to kind of ask this question, what value does each model add to the ensemble? The newest feature of these models, the catchment and the NOAA MP, are the existence of a groundwater module. And that is what I want to focus on for drought in the next few slides. Okay, so, and by the way, this is against USGS well data anomaly correlation. So just as an example, there's many more evaluations that we've done. I can't show them all today, so I'm just giving you a flavor as we move forward. So Yulong did a study, Yulong and David and others, where they compared 3 of these new groundwater scheme models. One of them is also the CLM, the community land model from NCAR. That's shown here as a purple line, and then NOAA MP and catchment are shown as red and blue lines. And the bottom line, this is a pretty busy figure, but the bottom line is that they compared it to GRACE data, the terrestrial water storage from GRACE, and they compared it across different river forecast center basins. And what they found was that all these models performed pretty well. You can see the dots are the GRACE data and the lines are the models, and in general, they look pretty good. And then you've got some anomaly correlation scores up above, which are all pretty high. There's a few areas where these models have challenges, like the Northeast River Forecast Center, but overall, the performance is pretty good, and they're pretty similar across the models. So, we're looking at having groundwater in the next generation of NLDAS. So one of the reasons we care about groundwater has to do with being able to monitor drought, and specifically being able to monitor drought recovery. So this is an example I wanted to show you because we talked about this on a previous drought telecon. There were all these concerns that in California they were getting all this rain in January, yet the drought monitor kept saying that drought persisted, and people were questioning why that was. Well, if you only look at root zone soil moisture, which is shown here from NOAA MP, but I can tell you these results are pretty similar to all the other NLDAS ensemble members. You can see that clearly the root zone was very wet, okay? And so people were asking, why does the NLDAS drought monitor show that everything is recovered, yet the drought monitor is not? And of course, the drought monitor takes into account many sources of information, including groundwater data from wells. And so what you can see over here is that if you have NOAA MP, in both of these cases, you still have areas that have substantial low percentile groundwater, and that's because the groundwater takes longer to recover, and it can take much, much longer to recover. So this is just one example of where having the groundwater schemes actually makes a big difference in terms of drought monitoring. So we started looking at other droughts just to see how we did for those. And so, what you're going to see is over here are the NLDAS operational LSMs, and over here are the ones we're testing, NOAA 3.6, catchment, NOAA MP, and VIC. You can see, like, for this example, things look pretty similar, not a lot of change. But what you notice is, if you actually look further at the groundwater side, and this is NOAA MP, this is total water storage over here on the left, and these 2 arrows are pointing to areas where up here, the root zone has a big anomaly, sort of in the northern and eastern part of this domain, but in the southern part of the domain, it's the groundwater that's really controlling maybe some of this ongoing drought. And so it's really the combination of the 2 that gives you the strength for monitoring. So that's similar to the California case I just showed you. So we were all excited, and we're like, oh, this is great, NOAA MP is going to be awesome. So then we looked at the Texas drought. And it turns out, and we've studied this as part of the Drought Task Force, and it turns out for this particular case, we couldn't explain it, but the NOAA MP, if you look down where my mouse is pointing, this one had much wetter conditions than what you expected to see, across all the other models, and that actually degraded the ensemble as well. And so we started looking at this to see what was going on, and even across the groundwater and the root zone, there tended to be not as deep of an anomaly as we expected. And so we are looking into this more, but some preliminary analysis is showing that in this particular case, we think that the coupling between the groundwater and the root zone is very tight in this particular groundwater model because it's based on top model. And so we do need to think more carefully and look at how that coupling is behaving and make sure that the parameters are well described in each area, because that coupling can have a big role in terms of where you monitor, where you expect drought to occur. Okay, so I can't go into much detail, but let me just sort of to wrap up the idea of an ensemble and what's the value to an ensemble, we have a paper we recently submitted where we looked at basically the contribution or the similarity of each model to the overall ensemble. And the idea is if a particular model is very similar to the ensemble, then it doesn't add much value. You could basically use that one model to represent the whole ensemble. So there's two ways to look at it. And generally for drought, you expect that having an ensemble is more skillful because it does a better job with extremes. So the first thing we did was we looked at, in this case, we're looking at the entire distribution of soil moisture, and we're asking how well does each model represent that distribution. And what you can see is that these, on the left column are all the NLDAS 2 models, and on the right column are all the new ones we're testing. You can see that NOAA MP, especially in Texas, is somewhat anomalous over the entire distribution. So there's something going on there that we need to look at, and that may be why it didn't do a good job detecting the 2011 drought. But NOAA 3.6, I mean, is almost a perfect representation of the ensemble, which more or less says that you could use NOAA 3.6 and you would capture the entire ensemble. So there's something going on there that we need to understand better. But what's interesting is if you look at the driest 5%, the 5th percentile for soil moisture, which kind of corresponds to roughly like a D3 or D4 drought, what you see is that they actually become quite different. And NOAA 3.6 still is mostly red, which means it does reflect the mean, but there's certain areas like the Northeast where it doesn't reflect the mean. And so having other models like VIC in the ensemble, for example, are very important for getting the full representation of these dry conditions. Similarly, for NOAA MP, you can see in the Southeast, it does an extremely good job representing things. So I think it's important to look at the full distribution and to then look carefully at the extremes when we're considering the value of an ensemble. And to wrap up, the last point I wanted to make is that we've spent a lot of time looking at different physics, but we haven't spent as much time looking at the other sources of uncertainty or the other sources of information in this ensemble. And so we published a paper last year with Graineering where we showed that for the NLDAS ensemble, there's basically 3 ways you lose information. The first way you lose information is from the forcing data, which is the boundary conditions. The second way you lose information is from parameters. And the third way is by the model physics. And when we analyze the NLDAS ensemble for soil moisture in the top 10 centimeters and specifically for the top 1 meter, which is really important for drought monitoring, what you found is that, you do lose some information from the forcing, but not a lot. So the difference between this bar and this bar is the loss of information due to forcing. The biggest drop is this bar to this bar, which is the loss of information due to parameters. And so for soil moisture, it's probably pretty clear to most people that we really do need to spend a lot more time on the soil parameters for drought monitoring because that's where the information is getting lost. And if you compare this to this last column is the loss in information due to the model physics. And you can see that the model physics, the loss of information there is much, much less than the loss of information in the parameters. So we do need to spend that time on the parameters as well as the forcings because, for example, for evapotranspiration, forcings are where you lose all the information. So my time is up, so I need to conclude, but I wanted to just summarize that, we're considering new models for NLDAS 3, and they tend to have pretty similar behavior with each other. As I showed in those bar charts, there's slight improvements in soil moisture and runoff, but overall they're pretty similar to each other. But one of the key findings is that schemes with the groundwater may help improve our representation of drought recovery in particular, but we need to watch out for the coupling between the groundwater and the soil moisture because it may be too strong in certain cases. And we need to spend some time looking not only at the physics, but especially at the parameters in these models because we know that we're losing information in the parameters for soil moisture. And that's it for me. Thanks.
Great. Thanks a lot, Krista. That was a really nice overview. Again, if you have a question online, please send me a chat message and let me know. I can unmute you and you can ask Krista your question. Are there any questions in the room for Krista? I have a question, Krista. So early on you showed a comparison between the drought monitor categories and you know, a simulation of that from NLDAS. Can you talk a little bit about like whether there's a time differential between one product and the other, you know, a lag between the you know, monitor and the NLDAS product?
Yeah, so, well, the NLDAS product comes out about 4 days behind real time. So there are, one of the things we are working on with NLDAS is to bring it up to real time. But in general, you know, the drought monitor has its, you know, its schedule, which is sort of, I guess, weekly, right? And so, you know, so there is some phase lag in the NLDAS outputs versus the drought monitor authors, you know, deadlines.
Yeah, and I guess what about in terms of, you know, identifying drought emergence in some of these cases, like you looked at the Texas case or the Southeast case, in terms of actually like getting the signal of the drought to emerge in the monitor versus NLDAS?
Yeah, so I think the best example from that one was the flash drought case in 2012 in the Midwest. And I mean, overall, I think that the soil moisture-oriented drought monitors pick that up before the vegetation-oriented, like quick dry, for example. But then there's work that has shown that the most timely information comes from the thermal remote sensing data, like the evaporative stress index, because that's where you first pick up the signs of stress. And it's sort of, you know, as the drought deepens, you know, you can start as a sort of an anomaly, a stress anomaly, which then translates to a soil moisture, a surface soil moisture anomaly, and then a root zone soil moisture anomaly, and then finally a groundwater anomaly. So I think all these metrics are useful, but I think, you know, what I'm noticing is that I guess we do need to pay more attention to the timing for both the detection and the recovery phase, because you can see here from this example, clearly the groundwater is going to be slower to recover. So, and I would expect the same is true for some types of vegetation, but not all. So we have to be careful about how we interpret the different sources of information. I don't know if that gets at your question, but.
Yeah, definitely. Thank you. Yeah. Anybody in the room think of a question? Okay. So I haven't seen any questions online, but that was really great, Krista. Thank you for presenting.
Thank you.
Okay, next speaker is Ed Clark. Ed, are you on the line?
I am, Dan.
Okay, great. I am throwing presenter privileges over to you. So, yeah, you can share your screen with us.
And let me know when you see my title slide.
Yeah, looks good.
All right. Well, thanks, Dan. Appreciate the opportunity. I want to first start off with thanking the team that's put together the National Water Model. It's not just the folks in the Office of Water Prediction and the National Water Center. It's a wide range of folks that extend out to NCAR, including the principal developer of the framework for the National Water Model, which I'll get to in a little bit, Impetus. This has truly been a community effort, and I think the results and the enthusiasm about the model, both from a scientific standpoint and from a programmatic standpoint, really reflects that community-based approach. Part of the impetus for the National Water Model is, as many of you on the call understand, a growing threat of hydrologic and water resources-related challenges across the nation. In fact, we came together with 3 other federal agencies, the Army Corps of Engineers, U.S. Geological Survey, and not initially, but since that time, FEMA, to look at the grand challenges facing the nation in terms of water and water-related resources. And these are, as you would expect, threats from a growing population, changing climate, non-stationarity, and increased variability. As we see in critical events year after year, ranging from city infrastructure to deliver water information to some of our most prominent storage units in California just this past year, and aging infrastructure is challenging the ability for humans to really harness the power and the resource that is our water. And finally, the socioeconomic risk associated with floods is continuing to escalate. If you look at decadal over decadal losses in between the 1980s, the 1990s, and then in 2010s, we saw rises up to the on average, $10 billion a year loss of flooding, direct impact of flooding alone. So it's certainly an escalating threat, a complex threat of multiple challenges. We also, the launch of the National Water Model also follows a period of engagement with the National Academies of Science. And in 2012, the report referenced here, Weather Service for the Nation Becoming Second to None, had some pretty tough news for the hydrology program, the Weather Services hydrology program, to swallow. And for someone like myself, who spent the better part of 2 decades working in that program, being mentored by many of our leading developers, it was challenging. And one of the findings was that there was a significant gap between the state of hydrologic science employing the current operational hydrologic operations and that which existed out in the academic and research community. And the recommendation was to improve pathways for collaboration and accelerate the ability to conduct research to operations. And that certainly transcends to the theme of this conversation today, which is evolving us towards a unified water modeling perspective. I would offer that the National Water Model itself is beginning to be that technological foundation for a unified approach that we are actively engaging with folks like Krista, Mike Eck, Dr. Gotchis, and others across the entire enterprise that is water and water resources modeling. And finally, this is key to any component. The recommendation key was that as we expanded our capabilities to side-by-side stand up and establish a commitment to thorough hydrologic prediction skill assessment, so standing up a water resources evaluation framework. Concurrent with this, the third driver in our launch of the National Model was a concurrent series of stakeholder engagements where we worked with water basins across the country, from the Hudson to the Delaware to the Potomac to Susquehanna to the Ohio, and out west into the watersheds in the Russian River Valley and Napa Valleys, to really ask them what are the hydrologic or the water resources challenges that keep you up at night. And unsurprisingly, it wasn't just flooding. It was issues and challenges that related to flooding, water quality, water availability, drought, all of which are exacerbated by climate change, climate uncertainty, and all of which there was this kind of cross-cutting need for integrated understanding of both the near-term and long-term risks. Further, the stakeholders in which we engaged really hammered home the need for street-level information, the information that allows them at the reach-by-reach, neighborhood-by-neighborhood, street-by-street level in order to respond to these varying types of hydrologic extremes and hydrologic threats. And finally, the stakeholder groups have really matured in their understanding of other applications across the weather enterprise of social science, and really hammered home the requirement or their desire that we included and leverage the best of social science as we move forward with the development of new capabilities, new predictive and environmental intelligence analytical type services. Finally, in the last 2 years, there's been a tremendous amount of interest, not just within the National Weather Service and the Office of Ocean and Atmospheric Research, but across all of the NOAA line offices, looking at the culmination of an improved cross-cutting water services spanning each of the various line offices. And this really culminated in the NOAA Water Initiative that was finalized in just early this year in 2017, and it was based off of 18 months of extensive work by the ad hoc NOAA Water Team, which was comprised of representatives from Fisheries, OAR, Weather Service, Ocean Service, amongst others. The Water Initiative itself is user-oriented, informed by regional and national water conversations. We held 2, one in California, one in Tuscaloosa, Alabama, and then a third national conversation where we really continued this commitment to working with the stakeholders. The Water Initiative itself leverages my center, the National Water Center, as a catalyst for next generation science and science-based information. And what I would, again, offer as an opportunity to glimpse how a unified modeling approach could be undertaken for NOAA as a whole. And finally, it calls for further collaboration, even beyond where we were with IRIS, the Integrated Water Resources Science and Service Consortium, to really expand collaboration across the federal enterprise and across the national research infrastructure. Key components of the National Water Initiative, improving modeling and prediction, and that's certainly one of the commitments we've made in the National Water Model. Enhanced water-related observations, accelerated research and development, strengthening the decision support tools that are provided both to developers and researchers, but also to the field who need to deploy 21st century data analytics strategies in order to take advantage of information coming out of these very high spatial and temporal fidelity models, producing on just one variable over 1 billion discrete pieces of information a day. An enhanced commitment to service delivery involving the communities and the stakeholders as we roll out new information, all of which is informed by the need for robust social science. So how are we going about doing this? Over the last 2 years, we've been successful in receiving funding, additional appropriations, directing us to first develop the centralized forecasting demonstration, an effort that through which the National Water Model was demonstration development and actual operationalization, as Dan mentioned in the introduction. The beginnings of the centralized water resources data service, or water resources data service, to provide comprehensive access in 21st century machine-to-machine techniques, communication techniques that not only provide access to the output from the National Water Model, but also to the core high-value forecasts produced by the river forecast centers today, both in their deterministic and probabilistic approaches. And finally, reaching back to that commitment to thorough and robust evaluation as we improve and bring new science online is this notion of a water resources evaluation service. In 2016, we were able to add on this enhanced water prediction capability, which we are just beginning the real technical work, looking at hyper-resolution modeling, real-time flood inundation linked back to a National Water Model capability, and are the first fleshings out of a enhanced impact-based water resources decision support services. I'll draw the attention on the first 2 bullets here in this purplish column. The hyper-resolution modeling and the real-time flood inundation mapping component are 2 themes of our engagement this summer with the academic community, a program that I run out of the National Water Center called the Water Center's Innovators Program, and this 7-week associated summer institute. We'll have 35 students from across the nation looking at the glimpses into the future of both hyper-resolution modeling and novel techniques for linking flood inundation libraries to large-scale, spatially continuous distributed hydrologic models. Finally, in 2017, we had proposed, did not receive appropriation or authorization, but had proposed the beginnings of the integrated water prediction capability. I should note that all 3 of these investments are resourced for 5 years, giving us enough time and enough resources to really build out comprehensive programmatic transformational change. And in 17, that transformational change included not only the establishment of the National Water Center Operations Center, creating a true center reach-back capability for supporting the river forecast centers and weather forecast offices in a way that the hydrology program has never been able to do in the past. It also included the scientific and developmental work to couple output from the National Water Model with modeling efforts undertaken by NOS, and potentially even by the Great Lakes Environmental Research Laboratory, GLERL, looking at the 4th coast or the North Coast in terms of the hydrodynamic circulation models necessary to represent critical water modeling elements in those regions. And then finally, in order to do this, coupling of the terrestrial, freshwater, riverine hydrologic modeling with the coastal applications, there was line items for increased high-performance computing capacity. Again, as I said, this was all proposed. It was in the President's FY17 budget, and as we look forward to the next month or so of uncertainty, we remain somewhat hopeful that we may have this opportunity. If not in 17, perhaps out into the future, because these types of coupled freshwater, saltwater processes, the threat of floods in the coastal zone, both from surge and from riverine flooding or backwater flooding, there are threats to the nation, and the citizens who are impacted by these events really don't care if the water is salty, brackish, or fresh. I want to get into the heart of the National Water Model itself. As I said, we launched this model in August 2016. I should note that it was really a miraculous level of effort led by my project lead and program lead here, Brian Cosgrove, who spent an exorbitant amount of time, a lot of late night emails, really accelerating the implementation of the National Water Model. This was launched in August 2016. I believe we began testing on WCOS in May of that year, and made our deadline by the end of FY4, or the end of the quarter 4, fiscal year 2016. So what is it? The National Water Model is operational Streamflow guidance. It's not the replacement to the forecast, it's additional guidance values for over 2.7 million reaches within the National Hydrography data set, or NHD Plus version 2. This is a topological relationship of the names of the rivers, streams, of the nation's rivers and streams, my apologies, that have comprehensive connectivity from the headwaters down to the main channels and out to the connections with the coast. This framework was chosen by, was adopted not only within NOAA, but across the agencies and entities that participate in the Open Water Data Initiative as a first cut of an authoritative hydrographic network for the nation, so that we use one relationship to describe the locations of rivers and streams across other infrastructural community level geospatial information data sets. The National Water Model is based, as I said, off of the WARP Hydro framework. This is developed by the folks at NCAR, led by Dave Gotches, really over the past almost 15 years. It's been adopted and demonstrated in Israel, Romania, and Italy. It's an international community-based approach, and it leverages many of the principles within the Unified Earth Modeling System framework. So it sets us up nicely for applications or extensions into a unified water modeling strategy. And as I said earlier, the model itself is rounded out with capabilities from both the Water Resources Evaluation Service and the Water Resources Data Service. The image on the left is the density of the current existing advanced hydrologic prediction streamflow gauges. They're visualized there as different colors on the network. And the image embedded in that is the density of the hydrographic information. By left, I meant right, and up is down. So, So what is the model itself? Well, this is a one-way coupling between the numerical weather prediction models running within the NSEP's Environmental Prediction Suite to a version of the NOAA MP land surface model. I believe this is approximately approaching the code version available in version 3.8 of NOAA MP. From there, it's a coupling with a terrestrial and terrain grid model running at the 250-meter grid level. That's then pushed into both on surface and subsurface using Boussinesq routing, and surface using a kinematic wave into the channel, that NHD Plus channel. From there, there's a simplified reservoir approximation of basically a bucket, a fill and spill bucket, as well as Muskegon Coonage that routes water within the reaches out to the catchment. And I will say that many of these choices were done out of the need to accelerate the implementation of the water model. Others, like the commitment to using NOAA MP, are part of the core components of the water modeling suite. But some, like the routing in particular, will likely change and be upgraded in time. And certainly, from the reservoir perspective, we view National Water Model version 1.0 and even 1.1 as really being applicable to the headwater points. This is not a full representation of the anthropogenic processes that are so critical to capturing our nation's water and water resources. Talking about the temporal range of the forecast, there are 4 cycles, effectively an analysis cycle that runs every hour, as well as a short-range forecast that goes out 15 hours into the future, and in release version 1.1 will go out 18 hours in the future. It's forced with MRMS, quantitative precipitation estimates, as well as the full suite of the high-resolution rapid refresh atmospheric forcings. Now we look at this as providing additional guidance to flash flood applications in very fast responding areas. The medium range forecast, currently running once per day, but will go to 4 times per day, goes out 10 days and uses downscaled GFS global forecast system information. Again, this is done on the 1 kilometer land surface model and 250 meter grid, and then full routing over the NHD Plus network. And finally, there's a long-range forecast that is a placeholder for improvements in water resources management predictions and services that leverages the CFSV2 downscaled 16 members of the CFSV2 run out to 30 days. The difference here is that in addition, this does not add the 250 meter routing. It simply takes the the runoff from the 1 kilometer land surface model, pushing to the channel, and pushes that channel downstream to downstream. I want to give you a sense of what the outputs from the National Water Model look like and why we talk about the scales, the street level scales, and how we get to that. This is the progression through the water.noaa.gov web presence, which is the home of the National Water Model, and you really get a sense of the revealing of the density of information as you go from national to regional to neighborhood, and then clicking in on the actual hydrologic interrogations at the stream scales. It's not just Streamflow. It's a full suite of water budget variables, soil moisture, snowpack, evapotranspiration, and some emerging ways to look at nuisance or even large-scale flooding events with this notion of ponded water, water on the surface. This is just a glimpse of what's available. The full details are at this water.noaa.gov address at the bottom of the site. As I said, we're standing up a water resources evaluation service, and in order to accelerate the deployment of the National Water Model, we had to take a little bit of a shortcut or delay in implementing the evaluation capability. Nevertheless, the team led here at both the Office of Water Prediction and down at the National Water Center has done a significant amount of episodic-based as well as some comprehensive evaluation of the water model at the gauges 2 reference basins, or about 1,700 gauges at areas of unregulation across the country. They are wrapping that work up, and we look forward to perhaps another opportunity to share a more thorough evaluation of the National Water Model. In the absence of that, many of what we're seeing today focuses on the skill of the model and the capability to provide guidance in areas that really haven't had objective hydrologic guidance in the past. These are areas where my colleague Brian has coined the phrase hydrologically blind or hydroblind to really highlight where interactions in hydrology between communities and citizens happen at a scale that is beyond the capabilities of where we are today with our existing forecast capabilities. And so as such, not only are we seeing interesting and promising performance from the water model, we're also seeing that the water model serves as not a replacement, but as a complement to the predictive capabilities deployed at our 13 river forecast centers. And that's really, really important to keep in mind as we go forward. I want to share with you just one last animation, and this is to me what illustrates kind of the leap forward and what the water model represents. This is an animation. This was an animation. This is an animation of Hurricane Lee and Tropical Storm Lee from 2011. This is leveraging a 30-year retrospective run using the NLDAS forcings over the domain from about middle of August to middle of September. And what you see here is a comprehensive response of the basin into and out of the coupled coastal ocean estuary environment. So I would say, well, today this is not necessarily a coupled model. It portends the ability to couple with modeling processes that are already evolving or already evolved in the circulation models that run within the Chesapeake. And we now have the capability to link that from treetops and bedrock summit to sea for watersheds across the nation. I think it's an exciting glimpse of what it means to model the nation's full network of rivers and streams. So I'll stop here. In summary, this is really the first step in transforming NOAA's water predicting services. We're building a foundation for change. This is an investment in modeling structure that is expandable and extensible. It provides the opportunity where we, in the past, did not have capabilities to both provide the street level hydrologic information at the level which our stakeholders require, as well as do the scientific linkages and the evolution with plans for activities like unified modeling or coupling with the coastal ocean estuary environment through our colleagues at NOS and up in the Great Lakes region. This is facilitated by the new organization, the Office of Water Prediction, and the advent of the National Water Center. And in particular to the National Water Model, this is becoming a state-of-the-art capability for robust water intelligence. It establishes the foundation for sustainable and improved investments in modeling that leverage the information that's coming back to us from an evaluation capability. We are committed to as resources allow, an annual update to this. So version 1.1 will be implemented later this spring in the early summer timeframe, with an annual release versioning targeting about the beginning of the water year each year going forward. And there are long-term efforts to fully leverage this investment with coupling with the coastal models, exploring at even higher resolution domains, extending the model capabilities to couple with groundwater for low flow and drought issues. And then the holy grail of this is called out in the NOAA Water Initiative, is adding in the right amount of information that make for robust and objective linkages to water quality applications. Certainly a tall order, but this is a really exciting time in the hydrology program, both within the Weather Service and across NOAA. And I think that there may be an increasing level of opportunities to explore the applications of these new techniques as we go forward. So Dan, I will wrap up. I'm happy to take any questions.
That's great, Ed. Thanks a lot. That was a really nice overview of a bunch of integrative activities that you guys are doing. So any questions in the room for Ed?
Hey, I do. Hi, Ed. Paula Davidson. How are you?
Hey, Paul.
So I wondered if you had in your longer range plans testing with NGGPS output somewhere in the future.
Absolutely. As we are forcings agnostic, and as NGGPS comes online and we can show improvement, which I expect we will, in downscaling those forcings as input to the National Water Model, it will absolutely be on the development pathway for where we evolve the Weather Service as a whole. The same I would say goes with the National Blended Model. That as those forcings are shown to provide value over what we're using as right now is raw output from the HER and the GFS, we'll consider all options that are on the table.
And just one follow-up to that. Yeah, I imagine that's a couple of years out before you get that kind of data to test with. But how are you using the ensemble information for Precip now? Are you using a particular model only, or are you using an ensemble product?
So the only run of the National Water Model that leverages ensembles is the 30-day run, and we use 16 members from the CFS V2. Everything else is deterministic. And again, that's based on resources and availability and compute. I would love nothing more than to have a perfect reforecast of the HER and the GFS and the ability to spin up the National Water Model and that type of a hydrologic ensemble forecast system capability.
The probabilistic information that you would supply for IDSS right now is based on post-processing by your river forecast?
Yeah. Yep. Yeah, we're using a time-lagged ensemble approach for both the HER and the GF when we have 4 members of the GFS daily to come up with a range of uncertainty for any given hours or set of hours response.
Okay.
Thanks, Paul. Jen, do you have a question?
This is Jin Huang from CPO. Question, so the current water model has NOAA MP as the physics. So have you tested the sensitivity, like if you have compared to other models? For example, how does water models drought monitor compared to NLDAS?
So we have not done inter-model comparison between different LSMs. One of the activities that was undertaken by the Office of Water Prediction was to take the simplified version, or the extended version of SAC HT-ET and SNO 17 models and place them into a research version of the WRF Hydro Code to facilitate that type of intercomparison. But really, in order to meet our congressional mandates to have the centralized demonstration and in the time frame, the accelerated time frame afforded to us, we really did not have time to do inter-land surface model intercomparisons.
Ed, there was one question from the chat. This individual is from Bill McDavid. He was asking, are you aware of any flood control dams drawing down their reservoirs in advance of a high flow event that the model predicted?
I am not aware of that level of interaction by stakeholders. Really, we're at the level now where the river forecast centers are providing a set of eyes on the model output, highlighting some challenges that we still face, as well as some opportunities where it's done well. I have not heard of any specific actions taken by stakeholders, particularly in regards to drawdowns of dams.
Okay, thanks for the question, Bill. And Ed, thanks so much for the presentation. That was really great.
Absolutely. Thank you very much.
Okay. Next up is Gabriella. Gabriella, are you on the line?
I am.
Okay, great. I'm transferring control over to your computer.
Right.
And so if you could, okay, great.
Hopefully it works. Okay. Can you see the right screen?
Yeah, it looks good. Whenever you're ready, go ahead.
Perfect. So, Gabriele Villarini, the University of Iowa, thank you very much for having me here. And today what I want to do, I want to present some of the work that Luis Leiter, former postdoc in my group, and myself and Alan Bradley in particular have been doing related to the NMME forecast, looking at evaluating this forecast both at the monthly level, but also looking at extreme events, and I'll talk a little more about it later on. But you can see a picture of some of the events we've analyzed, and so we focus both on floods and droughts. The analysis, the study regions that we considered are the continental United States and Europe. We have divided the United States into 7 regions, these 7 macro regions for which I will show the results. And we have divided Europe into 4 regions based on the Köppen climate categories. And so you can see them in here. As far as data, we have used 8 of the available NMME models. This is the list with some of the main features of these products. When we list the periods or the ensemble size, this is an upper bound. Some of the models had gaps, and not all of the ensemble members had continuous data. So you can view this almost as an upper bound in terms of data availability. I'm going to start by talking about the evaluation at the monthly scale. And in general, when we think about one way in which we quantify the skill of these models is in terms of correlation coefficient. And so we have seen the many maps showing the correlation coefficient between the forecast and the observation. What we have done, the metric that we have decided to use, is one in which the correlation coefficient is actually decomposed and penalized for the presence of biases. What you would see in the top left panel is what we would call a high-quality forecast, with the forecast and the observations showing a strong linear relationship, and this linear relationship aligns along the one-to-one line, these red circles in the top left panel. Now, if you just compute the correlation coefficient of the top right panel, you would actually get the same exact correlation coefficient value, despite the fact that the points are no longer aligned along the one-to-one line, but they're shifted to the right. And so in this case, you have an offset, and the correlation coefficient is affected by unconditional biases. Furthermore, you could have an even stronger linear relationship in the bottom left panel, but one such that it doesn't align along the one-to-one line, which is where we want it to be. And so there is a slope issue. The linear relationship is tilted with respect to the target one-to-one line. And then finally, we have this poor association, where there is quite a bit of scatter associated with this with between the forecast and the observation. So what we have done is we have used the formulations that allow us to decompose the skill, and I'll refer to this as actual skill or SS or score skill, into three components. One, which is the PS, the potential skill, which is the coefficient of determination between the observations and forecast. What we do, though, is that we penalize the coefficient of determination for unconditional and conditional biases. You would see this as SREL, the slope reliability factor, quantifies the presence of conditional biases, basically the sloping with respect to the 45-degree line. And then you have a standardized mean error, SME, which quantifies the biases or the offsets with respect to the one-to-one relationship. And so the results I'll show are stratified according to these four different metrics. We're going to start with the U.S., and it's a busy slide, but it's one that is fairly intuitive to understand. On the columns, you have the 7 different regions we focused on. On the rows, you have the different metrics that we consider: the potential skill, the actual skill, unconditional and conditional biases. For each panel, you have the lead time from the shortest to the longest, from left to right, and you have the month from January to December as you move from the bottom to the top. In general, what you see is that the skill decreases rapidly. This is for temperature. Decreases rapidly as you increase the lead time. The strongest potential skill is for the shortest lead time, and then it decreases. No surprises there. Now, the problem is that this correlation coefficient, or the coefficient of determination, is not unbiased, but we have quite a bit of unconditional biases. You can see from the bottom set of panels, which affect significantly the actual skill, the skill score. You see that now it becomes much more negative, and it's less, it doesn't paint a very, there is room for improvement in a sense. One of the things is that this bias does not depend on lead time, but it has more of a seasonal or a monthly dependence. You see that the values across the different lead times, they don't really change. What they change is that there are certain months out of the year for which we see these stronger or weaker skills. For precipitation, the picture is very similar, just that the overall skill is even reduced with respect to temperature. So based on this, it appears that the largest biases are due to the to unconditional biases rather than conditional biases for what we have seen. Now, we can fast forward and think about extremes. So far we've talked about monthly data. What we've done is we have considered 4 floods and 4 drought events. The selection that we have made was such that we tried to have events from both the eastern U.S., central U.S., and western U.S. And the way we have defined a flood or a drought is based on the characterization in the billion-dollar disasters by NCDC. So over the study period, those were the events that we considered: the 1993 flood in the Midwest, as well as the 2008, and then 1995 flood in California, and the 2010 flood in northeastern U.S., for instance. And what you see is that we have identified the areas of interest, these colored pixeled areas, based on how anomalous the precipitation values were with respect to the climatology. And so what you see over there are all anomalies that are larger than 1. We've played with this threshold, but the results don't change very much. And so this figure gives you an idea of the areas that I will be focusing on in an aggregate sense in terms of the results, which are shown here. What you see again, top panel, you have flood events. Bottom panel, you have droughts. And by droughts, we look both at high temperature or low precipitation. The black solid line is the target that we want to, based on the observational data. This gray area are the 95% confidence intervals associated with that quantile. And here you have the 8 different models. This gray dashed dotted line is the ensemble average. And so overall, the routes tend to be better forecasted than floods. There isn't a very strong dependence on lead time, so the lead time goes from left to right within each panel. The shortest lead time tends to be a little better in general, but there is no real strong dependence. And overall, there is, at least it got in general the right sign in terms of the anomalies, but that's not always the case. Now, up to this point, we only focused on equal averages. So when we looked at the ensemble means, we only looked at every member out of the 8 models got the same weight. And so what we have done as a follow-up, we have started playing with different weighing schemes. I don't have the time to go into the details, but what we've done is that we have weighted the forecast based on historical data. We have based on historical data, and we have devised different weighing scheme. This is based on Bayesian updating. And what we focused on is the equal weights. So each of the 8 modeling centers gets the same weight. We have applied this Bayesian updating to each of these 8 modeling members, but then we have also said instead of computing the average of each member and then do the weighing, let's look at all the 94 members that are available and weigh them independently. Then we also said, well, if you think about it, not all the members are independent, not all the modeling centers have independent, the models can be considered independent, as some of those are newer version of the same model. And so we have applied the Bayesian updated on the principal components of the individual modeling center or the individual 94 members. And so you'll see that the naming scheme is equal weights, Bayesian updated applied to the 8 modeling center or to the 94 members, or Bayesian updating applied to the principal components. These are the results for precipitation. The left panels are for the shortest lead time. The right panels are for the 5.5-month lead times. This is for Europe. You see that there are the 4 different regions and the 5 different weighing schemes. The gray cloud in the back is from the individual models, individual members, and so I don't want to spend too much time on this, but what it turns out is that Bayesian updating allows to get more of a one-to-one relationship. One example is here, where you have more of a tilted lines slope relationship in this case, which tends to become more along the one-to-one line with the Bayesian updating. Surprising enough, working on the principal components, at least from the Bayesian updating, didn't really give us an improvement. Actually led to almost a deterioration of the results. We've done the same for temperature. Obviously, temperature tends to be better behaved. And in general, you get a slight increase in potential skill and a general increase in the actual skill. You can see it from here. Left panel is for precipitation, right panels are for temperature. The equal weights versus the Bayesian updating of the 8 models. Potential skill increases slightly when you compare one with the other. The nice element is that the Bayesian updating removes completely the unconditional biases, so basically it does bias correction. That comes at the price of introducing some conditional bias, which was not present with equal weights. Overall, the actual skill increases, or at least it's much less negative than what you would get from equal weights. We did the similar, we applied this to extremes for Europe. Extreme precipitation in the top panel, those are the 4 events we analyzed, or extreme temperature, and these are in the bottom panel. And just to give you an idea of the spatial extent of these events. when we look at predictability of these extremes, there is probably some room for improvement. We get, not surprisingly, that the larger the anomaly, the worse the performance is, or at least the difference between observations and forecast. Arguably, the equal average, equal weights, this black line, tends to perform consistently better than any of the other schemes we have identified. Now, you can find cases where one method works better than the other, but overall, I would say that equal weights works well. And just to wrap up, I'm going to leave the slide here, but the couple of take-home messages that I want to convey are that overall extremes, not surprisingly, are much harder to forecast than monthly conditions. Also that equal weights tend to work pretty well in general. Using the principal components doesn't really add that much, and that the Bayesian updating didn't really give us a huge bump in performance. Now, this is true for at least for precipitation and temperature over Europe. Another study that we have done looking at ENSO forecasting showed that the Bayesian updating increased the skill, increased the model skills in the shortest lead time from 1 to 6 months lead time compared to the equal weights. So we're still working on developing or improving the weighing schemes and trying to come up with even better ways of doing so. So with this, I'm going to wrap up, and I'll be happy to take questions. Thank you.
That's great. Thank you, Gabriele. So if you have questions online, please send me a chat message. I can unmute you or just pose your question to Gabriele. Any questions in the room here? I was just wondering in the meantime whether you've talked to the Climate Prediction Center or any staff over there about this work that you've been doing, as it's it's pretty promising for post-processing NMME.
Yeah, so I've been sharing the papers that we have been working on. Part of the work we've also been doing is looking at the applicability of NMME for streamflow forecasting from a statistical perspective, and the results are promising, and we are now extending it. We have done it as a proof of concept for one watershed, and now we are expanding it to about 450 sites across the Midwest. So, yeah, my approach is, so when we have results and results in a form that is understandable, I've been sharing them with folks over there.
Great. That's great.
So maybe one mechanism is to maybe present the results at the NMME telecom. So usually maybe make a special request.
Well, that's a good idea, yeah.
So Safety Wit or other forecasters can join NMME telecom.
Yeah. So
yeah, absolutely. And we are close to getting at least the preliminary results for the entire Midwest. And so once we have them, I'd be happy to do so. Thank you.
Yeah, you can maybe get in touch with Ben Kurtman about that. Yeah.
Absolutely.
Good idea. Okay, any other questions? Okay, well, thanks a lot for joining. That was really interesting to hear what you've been up to, Gabriele.
Thank you.
Okay, and finally, final speaker is Brian Wells. Brian, are you on the line?
I am on the line. Can you hear me?
Yeah, I can hear you, and I'm transferring control over to your computer. So if you could just share your screen.
You should see it now.
Yeah.
Cool.
And then just, yeah, great. Okay, yeah, whenever you're ready, go ahead, Brian. Thank you.
Well, thank you first off for inviting me. This might seem like a talk that's a bit out of sorts with the rest of them, so it's worth kind of setting it up a little bit, what our goals are and how it fits into what we've just seen. My group here in Central California has a pretty large focus on salmon, which are coming out of one of the greatest drought periods we've ever seen. And we're trying to do life cycle modeling. And what that means is that freshwater conditions such as drought or flooding for that matter can really affect the size, the timing, and the survival and hence abundance of salmon going into the ocean. So if one's to evaluate the effect of, say, drought or flooding or habitat loss in fresh water, you can't do it without sight of the ocean. To even put it in a better perspective, that first year survival of salmon appears to be the time, overwhelmingly appears to be the time that recruitment or ultimately the fishery abundance and escapement values are set. So our questions revolve around how can we understand the ocean to better mitigate or manage our practices in fresh water? When does size matter? When does abundance matter? When does fresh water matter? So in essence, ocean can serve to both help the survival and the problems in fresh water if the conditions are good in the ocean, or exacerbate them by actually synergistically, as we saw in 2005 and you'll see soon, it can actually work synergistically in a poor way. So what we're going to do here is in collaboration, and I've got to admit as well, I'm an ecologist, not a modeler, but we work very closely with a variety of modelers around the nation. And this exercise here is largely in collaboration with Jerome Feicher and Chris Edwards at UCSC here at Santa Cruz, just up the hill from us. So a large part of what we're doing with this ROMS model in this case is trying to understand if the reality of what we see in the boat matches what we're modeling in these modeling frameworks. And this is an assimilative model, so it does incorporate real data, but not the data we're actually comparing it to here. This map here to the left is Central California, and we can divide this by shelf, which is generally inside this line, offshore, and then Monterey Bay. And what I've done here is I have Monterey Bay, shelf, and oceanic in these columns, and we're looking at the temperature from the model, salinity from the model, something referred to as 26.0 isopycnal depth, which is really a matter of nutrients availability to the surface, which is important for kickstarting all of this productivity. And then stratification, which in large part is a similar value of getting nutrients to the surface. The key of this figure, without getting into all the details, is we sampled all those spots seen on the map to the left, categorized them by area, and what we see is the real data from the ship surveys in the gray in each one of these plots. And the point is, spatially, on the shelf, we can focus there. On the shelf, we see that temperature in the model in the black and CTD data, live empirical data, are actually matched up very well. Same with salinity, same with isopycnal depth, and same with stratification. The point of this is that spatially, on the shelf, across the years 1987 to 2009, we were able to actually match what we saw live to this assimilative product. And the case was also true for Monterey Bay and the oceanic system. So that gave us some confidence that physically we can describe what is going on in a given location. But these are yearly samples taken each spring, and it tells us nothing about what these models can do between days or months. And that's what I've done here. Well, what Isaac Schroeder has done here. We have our temperature, salinity, isopycnal depth, and stratification yet again. The blue data comes from a mooring post in Monterey Bay. It just sits there and collects for us on an hourly basis, and this is divided to days. So it's days between year 2000 and 2010. And again, the take-home point here is that our modeled temperature, our modeled salinity, our modeled 26.0, and our stratification being the least, mind you, match very well. So in fact, now we can not only say that this model is capable of capturing the environment with any location, it actually seems, across most of the variables we examined, capable of capturing the variability from day to day as well. Now, it's worth noting, stratification here, that mismatch, and this is one of the problems that we deal with in these assimilative products in the ocean. The way it's been explained to me is if we're to assimilate a temperature data from satellite, then we're imposing a restriction on what the model can actually have at the surface, which then can feed down, stratification actually being a temperature profile, can feed down and hence alter it somewhat. So these types of examinations and comparisons, we believe, are critical for deciding which variables we have more faith in and which ones we have less faith in. And this becomes important because we move on from this point to actually start modeling the biological variability within our system. So what we can do is we can take these ROMs, and we have two different groups here. On the right, we've got the ROMs connected to what's known as cosine, carbon, oxygen, silicon, and nitrogen model. It's run out of Jet Propulsion Lab and GDFL, and it's basically Fei Chai and Yu Chao. What this model shows us on the right is that we can actually hook that model to their ROMs and taking it through the biological components, get all the way up to zooplankton, or in this case, krill abundance on the shelf along the coast. So we can actually model that krill each year, each day across the period of time that we have an interest in. But we can also, without even going to the modeled route, we can actually also take and look at the actual krill on the shelf, as shown here in this very plot here at the top. That's krill collected on the shelf from our surveys every May and June from 1990 to present now. And we can actually match that to the values we get for isopycnal depth and correlate it to isopycnal depths at sea throughout the entire year. Now what I've done is, it's hard to see here, so I apologize for that, but each one of these little dots you see here, in January, we've calculated an isopycnal depth from the ROMs. And we correlate this top time series, what we see in May, to that isopycnal depth. Now the key of this is that you don't see much correlation spatially with what we see in krill in January, what we see in May relative to February. But you do see critically that the amount of krill we get in May, that top time series, correlates very highly to what is an upwelling plume here in March. So in essence, what we can say is that if I go out in a ship in May, or more importantly, if a salmon goes to sea in May, its likelihood of having krill on which to feed is dependent on these oceanographic conditions all the way back to March. Now that's really cool, because what that does is it opens up a lot of cool questions, because it's allowing us to take these ROMs and actually understand what we refer to on the West Coast as preconditioning. In other words, salmon come out, and the salmon survival is going to depend on the food they have, but we can speak nothing about how that food got there. With ROMs, we can actually use that ROMs data to tell us how that real food got there from previous or evolution of the upwelling system. And again, we can also simply, if we trust it, hook up our ROMs to a biophysical model and directly allow that emergent quality to play out in simulated data. So not only do we believe, and we actually have evidence for, we are matching that krill distribution, much like we did with the environmental data, on a spatial value. We say it's on the shelf, near canyons. The model's working very well at giving us krill as an output, and we have an understanding from empirical data how that model is evolving to that point. We can actually look at the model each year and ask the question, just like I did with the environmental data, does it capture temporal variability? And in fact, it does. And this is again from the cosine value. Mesozooplankton, as observed, in this area right up here, this area B in that little map, that's the area to which salmon first emigrate when they come out of the Central Valley. They come to this area, and work that we've done in the past has demonstrated if krill is not there, salmon will die. So what we show here is that, in fact, what we see in the environment, T. spinifera, krill, correlates to what we model in the environment. So, in fact, we are able to match very well the amount of krill just by connecting the biophysical model to the ROMS model. So to this point, what I've said is we have a ROMS model that's assimilating data that we believe can spatially and temporally capture environmental time series. We can use those environmental time series to actually match up with the empirical data of biological series we have on the shelf and start telling a story about the evolution of that system. With that story in hand, we can actually now model the system through simulation and are capable of capturing in this framework the same things we're seeing in the real world. And again, the importance of this is that salmon, upon immigration, if they do not intersect the appropriate amount of krill, they will die. So to kind of give you an idea of what I mean here, we've got a coast-wide survey for salmon along this entire grid here. Well, it turns out in the year 2000, we had an incredible survival of salmon. It was a boom year. It's what we always like to look back at and say, oh, look how far we've, how far we've fallen. But in fact, it's so above average, it's not even a fair year. But that's good for what we're doing here in terms of modeling. 2005 was a year of incredibly poor salmon survival. A crash year, actually. We ended up closing the fishery for a couple of years. And the cause, we believed, after a full examination, was not freshwater, but ocean conditions. And for the first time, we actually show that here. What we've done is we've fit a habitat model to salmon. We basically said salmon like a certain diatom level, krill number, temperature, salinity. We've built out this pretty complicated model to build potential habitat for salmon at sea. In 2000, you'll notice there's this big red area of very high-quality environment where salmon come out. In 2005, there happens to be one giant hole there. So again, with what we understand of the emergent quality of the system, the evolution of the prey base, and then using these models in concert with what we see in terms of where salmon like to exist, we can actually start understanding how the environment's affecting salmon once they get to the ocean. We can take this a step farther. What we can actually say is that we can connect our ROMS NMME, which is that model from UCSC Jerome Fisher specifically, to an individual-based model for salmon behavior and a dynamic energy budget for salmon growth. What I mean by that is we allow particles, little salmon particles, to come to the ocean, and they move in an increasing gradient of the krill that they experience. And then using a dynamic energy budget, which accounts for temperature and krill, or consumption of krill, and size of the fish at any given time, we can allow that fish to grow. Now, going back to something I said earlier, during poor ocean conditions, fish that either come out of freshwater small or don't grow quickly enough in the ocean are prone to increased mortality through predation, most likely. So let's actually look at how fish are expected to grow and distribute during years of high survival compared to years of poor survival. During years of good survival, the salmon come out, and they actually have incredibly broad distribution over large krill abundance locations. This is the distribution of krill as well. And you can see with colors where the fish are, and the more red they are, the better they're growing. Key there is, during years of good survival, when these particles come to the simulated world, they're experiencing very good growth, which we can then associate with survival. During 2005, we can see they're much tighter along the coast, the fish, as they come to the ocean, and their growth is actually quite poor. So that sort of is a great ending point in many ways. It says we can actually take these simulation models, hook them to a simulation behavior and a simulated growth, and in fact, when we actually compare what we see in the world to what we see in terms of our time series of survival and growth, oceanographic conditions, and prayscapes, it's truly matching. What's additionally cool is you can actually start telling a story about what the environmental conditions were that led to these poor survival years. The top figure is temperature from the model. Red is years of poor survival across the months. Red is the average temperature for years of poor survival across the months, January to December. And the take home here is that during poor survival years, temperature is still high here in March and April, which is typically the initiation of upwelling. In good survival years, in the blue, we see actually temperature drops very quickly, and initiation of upwelling. The key being, something tells us that initiation of upwelling, I'd like to remind you of that figure I showed you a long time ago, where I showed the upwelling characteristics in March off the point-to-point rays relate highly to the amount of krill we see on the shelf in May. And in fact, this model captures that evolution. Upwelling, you get an increase in blue, you get the good years of survival, you get an increase in phytoplankton early on. And then from May forward, you get an increase in zooplankton. So in fact, this model is capturing not only the evolution of the system, we trust its data from a physical and biological standpoint. We can incorporate salmon behavior, growth, distribution, and then look at that related to survival, and actually understand the system beyond what we could actually sample. I'll leave you with this figure. This figure simply takes the distribution of krill as modeled by that NMME and relates it to the survival estimates we have for salmon in the first year of life. And the real key here is that this tells us that not only does freshwater have a significant impact, but that this ocean survival is going to also be highly variable in the ocean and can be modeled with these approaches. So to wrap up, we had an evaluation of the model physics, spatially, and temporally, and we had success with that, a simulative approach. We matched it to what we saw at sea. We can actually use the ROMs connected to an ecosystem model to actually get good krill and prayscape features, temporally and spatially. We then used the model to basically build out what is the quality of habitat of salmon, which again could come from poor freshwater or good freshwater conditions. What are they going to experience? Will the ocean mitigate or exacerbate freshwater issues? We use an IBM to show now we're entering a framework where we can actually start really testing out these issues. And finally, we can actually, I think the best model I've seen over the years of looking at this, we can use these models to develop indices that can then be used as covariates in an analysis of understanding survival. I tried to be somewhat quick, and it was a grand overview. I hope that that was helpful, and if you have any questions, I'm very happy to take them.
Yeah, thanks a lot, Brian. That was really interesting. If you have a question on the WebEx, please send it via the chat feature. Any questions in the room for Brian? Brian, I guess I'm just wondering, what the eventual outcome of this is. Like, do you see, the potential for some predictive products within the California current system for this species? What do you think?
Ultimately, the goal will be, so there's a variety of kinds of management we have for salmon on the coast. We have a tactical approach where one basically estimates the number of salmon out there and then forecasts the number coming back, and harvest control rules are set. What we see this as is a module to hook into the freshwater models for strategic management. What I mean by that is, if we can look out over the 20, 30 years, had we changed freshwater flow to be X instead of Y, given an ocean environment, will that have actually helped the salmon in terms of variability, abundance, and overall productivity of the system? So we see the end product of this being the oceanic component necessary for evaluating freshwater strategies.
Okay. That's interesting. There was a question from Krista. Krista's wondering how ocean color obs like VEERS and potentially from PACE could be useful for evaluating the phytoplankton composition in the model.
This is where I have to punt to my collaborators. And what I can say is Chris Edwards, through IEA actually, was funded a postdoc that started assimilating some of these color satellite data for phytoplankton. Whether he's come out with that paper or not, I can't be sure, but I wouldn't hesitate to write him and ask.
Okay. Thanks for the question, Krista. So I'm not seeing any other questions. So Brian, thanks a lot. That was really great, and I'm happy you participated. Okay,
I really appreciate it.
Yeah, thanks a lot. So that wraps up this webinar. I want to thank the speakers, Brian, Krista, Ed, and Gabriela, for taking the time to speak today. It was, I think, a diverse set of topics. At NOAA, the context of water modeling is fairly broad. There's the hydrological element, but then also, things like what Gabriela talked about in terms of the forcing in the climate system and extreme events, and then both the dry and wet side of modeling the hydroclimate. And then, of course, NOAA has a huge mission in terms of marine ecosystems, and so I think Brian, gave us a sampling of some of the things that they're looking at the fisheries science centers in terms of modeling the connection between the physical climate and the ecosystem. So a lot of really great work, a lot of interesting opportunities for unification of the modeling systems and different applications of modeling systems. So I think it was really interesting webinar, and thanks for speaking. The recording of this webinar should be up by the end of the week, including the presentations. You'll be able to get those at our webinar website. If you happen to receive the announcement for this webinar from someone else, you can also sign up for our email list on the website, and you can see the recordings as well for the other unified modeling webinars that we held in the fall. And then the final thing I want to do is just thank Will Chong, who's in the room here. I think some folks online know Will. Will is moving on at the end of next week. He has a new job. He's going to be using his GIS skills for Tesla Government, which is a company that does some defense contracting, and we're really happy for Will. And in the context of the webinar, I also want to thank you because we started this about 5 years ago, and you've been really helpful in helping me figure out how to set this up and keep it running and all the IT stuff. And when I've been panicked at the beginning of webinars where things are not working, you've helped solve all of the problems. So I really wanted to thank you, and I know some folks online also know you well via email at the very least. So we will miss you and really appreciate all the help over the years, Will. So thank you. So anyhow, that's it for this webinar. Thanks again for joining, and stay tuned to our website for the next webinar. We'll have probably a couple more webinars before the season ends for this year.